Hello everyone, my name is Arun and welcome to my channel. This series is a series of tutorials on C programming, and in this tutorial we'll be talking about some three concepts that will be very important while debugging with programs that will show some funny input with respect to funny outputs. Okay, these topics are actually data truncation, data underflow, and data overflow. Now, suppose you're having some program, let's say, that ran perfectly for certain given values of 7 input values, and afterwards for certain particular value the program starts to give some funny output, let's say. Chances are that you might have come across this data truncation, underflow and overflow issues. Okay, let's look at them one by one. Okay, now what data truncation is that? Okay, internally or externally, when you run a particular program, let's say, when you run a particular program, uh, the data uh, the data types they undergo some kind of truncation while doing some arithmetic operation, all while being represented. Okay, for instance, right now I just commented these codes, only this line and this line gets compiled when I run this program. So if I compile this and build this and execute this, let's see what happens here. Since I1 is 5 and I2 is 5, when I print this statement, I get 5 divided by 5, okay, is 1. Seems pretty simple and legit, isn't it? Not a problem, right? Okay, so what I'm doing, I'm just taking 5 and divided by 5, and that result will be printed over here. 5 divided by 5 is 1, so it's okay. Now instead of 5, I'm just going to put this to be 6. So if my intuition is right, okay, by losing a mathematical knowledge, if you look at this it should be like 5 divided by 6 will be equal to 0.8333 something. That should how it should turn out to be, right? Now let's see. Compile this, build this, and execute this. Turns out it's turning out to be 0. Now this is a bit odd. What, it should not be 0, but why is it 0? Well, that's where you have to look into the details more carefully. You see these variables I1 and I2 are actually, they fall in the data type int. As a consequence, because of this data type, they should not have the inbuilt structure in C is such that these variables do not have any floating point during their operations. So when you take two integers and add them, the result will also be an integer. Subtract two integers, the result will also be an integer. Multiply them, the result will be integers. And even if you divide them, the result will be an integer. If suppose during the division operation that result does not turn out to be an integer, the protocol is that find the divide the numbers and then chop the decimal part off. For instance, let me open my calculator program over here, and then I'll explain this properly like this. So if I divide 5 divided by 6, I'll get this number 0.8333, so on and so forth. So what C does under the hood, because of the data type int, is that when you divide 5 divided by 6, you'll get this answer first, and then to make sure to convert that output into an integer, what it does is that it just removes this trailing part of the number. It removes the decimal part of this number. Once if this is removed, what it remains is only 0 remains. Okay, and 0 is a proper integer. Okay, so that's what it gets printed over here. So if I divide 5 divided by 6, it will be 0.833, and because it has to be an integer, that entire decimal part is chopped off and only 0 gets printed over here. Likewise, if I put an integer value nearby, I assign this to an integer value, that integer will also have the same issue. Okay, and this is something that is very common with programming language, many of the programming languages, so you have to keep this in mind very carefully. Okay, this is the one kind of data truncation. Second data truncation occurs when the number is not being represented properly. Okay, for instance, let's take these two numbers, these two. Okay, I have a value float a1, float value which a1 is set to be 5, and then I have another value a2 which is set to be 20.46. Now on this line, I'm just saying that 5 divided by 20.6 will be 20.46 will be equal to the corresponding division of 5 divided by 20.46. Okay, now if I compile this, build this, and execute this file over here, this 5 came out to be perfectly fine, not a problem. But look at this, 20.46 is instead of getting 20.46, we get 20.4599999. That's odd. This should be 20.46, isn't it? But why do we get like this? Well, turns out this is because of not because of our computational mistake. Rather, this is because of an internal data truncation that happens to represent numbers. See, where floating values have certain kind of numbers present inside them. Okay, it's like a certain number of bytes, and certain each floating data requires certain number of bytes to store them. So 4 bytes and anything like that. So in these bytes, certain number of bits. Okay, so if you have 4 byte float, let's say, you have 32 bits, and certain number of bits will be allocated to store these numerical digits, whereas the remaining part will be used to store the exponent to which the number has to be raised. As a consequence, okay, because of your number scheme that will be represented by these floating digits, floating variables, is not complete. You will have a lot of breaks in between them. So if you come across a particular number, let's say, which the bits cannot perfectly represent, what will happen is that the number which is very very closest to the actual number you specify will be represented. So for in this case, 20.46, though may be a simple number, okay, for this kind of a float argument, for data type, 20.46 will not is not possible to be represented perfectly by this floating data type. As a consequence, the number that is very very close to 20.46 in terms of precision, which is 20.459999, it gets printed over here. Okay, and that gets printed over here, and that's the reason why we are getting this number. And all the calculations, wherever you come across 20.46, instead of that, this number 20.459999 will be used in throughout the calculations. Okay, so this is actually another kind of data truncation, wherein unlike the previous case wherein to conserve the data type, okay, truncation happens here. The truncation happens because the data type is not able to perfectly represent this number, and that is the problem. This is because of an internal problem. Okay, now so one workaround for this problem is that use maybe a higher data type, maybe a data type that is more precise and has more I can give more significant digits well. So double could be a good way. So if I compile, build and execute this, now if you look at the result, 5 turns out to be fine, and 20.46, now it comes perfectly. So if you are working with some simple programs, let's say, and your precision is not you're not so picky about your precision, a number of digits being accurate, you can use float and then you get work around with it. On the other hand, if you're like very picky, or if you're doing excuse me, if you're doing some serious calculations wherein the numbers have to be you're very the calculations can be very sensitive to the rounding of errors like this. Okay, then in that case go for higher data type so that you don't get into this trouble. Finally, okay, these are the two types of data truncation. One, because due to the operator, okay, typecasting that happens in the operator to preserve the data type, and the second one happens because the values are not being represented properly. This is just one example. On the other hand, if you go with the higher numbers, let's say, you can come across several examples. And in the next topic we are going to talk about, we'll talk about these two together, because these are like twin problems, underflow and overflow. Let's look at them with this particular example. For this I don't need this, as I will need this. Okay, turns out this int over here, this int data type, okay, available in the version of C program that I use, okay, is actually 8 bytes if I remember right. Hold on, let me just check my Chrome. Okay, integer data type in C, and if you look at Wikipedia, okay, there are several data types available over here, By default it is long int. Okay, my mistake. My mistake. It is 4 bytes, not a problem. It is 4 bytes. Okay, so the I just written these two numbers over here. I'm defining these two integers. One of them with a value with this such a big value, another one with such a small value with a negative. Let's see. 2,147,483,647. That is a positive value for C1, and for C2 it's negative 2,147,483,648. Now what I'm going to do is that I'm going to add just one value. I'm just going to increment this C1 by 1, and I'm going to decrement C2 by -1. So if this happens, instead of this 7 over here, you'll come across 8, isn't it? Okay, instead of this 8, you'll come across 9, isn't it? Well, that's what our normally we'll think about, but this behaves a little differently in C. Now if I compile, build and execute this, check this result out. Now this is funny. Look at this. This number plus 1 turns out to be negative of this negative. Whereas this number -2, okay, it's not -2, sorry, it's -1. Regardless, it will work the same. Whereas this number -1 is actually a plus such a big number. Why did this happen? These are the classical examples of data underflow and data overflow. Now what happens is that each data type has a limit to it, has a maximum value possible that can be represented and a minimum value that can be represented. Okay, now for an integer that takes 4 bytes of memory or 32 bits of memory to store data, okay, this is the maximum value this integer data type can represent, which is 2,147,483,647. That's a maximum positive value it can represent, and the minimum value it can represent is that. So this is the maximum value, this is the minimum value, is negative this number. Okay, and now if I increase this by one more value, what happens is that this entire number trips, and then you go to the lowest value. Okay, you go to the lowest minimum value of that number series, and this is actually what you call as an overflow problem, wherein you reach the maximum possible number that you can represent with a given data type. And so if you add more data type or multiply that data type, or multiply that number with some other number, thereby trying to increase the magnitude, the polarity flips, the sign flips, and then the magnitude completely changes depending on the operation. So this is an overflow, whereas this is what you call as an underflow, meaning unlike in this case wherein you reach the highest value, you reach the lowest most representable data for the representable number for that particular data type, and then you go down by some more data trying to represent some number that is even lower, and as a consequence the data type trips, and then you go to the highest number that you possibly can represent in that data type, and then you go below subsequently like that. Okay, this is actually called as an underflow. One classical example where such underflow happens is that if you want, you can search this. You might have heard about this Gangnam Style, right? Gangnam Style YouTube crash record. You just type Gangnam Style YouTube crash, and then you will get a lot of videos regarding this. This is the one, Gangnam Style overflow int underscore max. Okay, you can read this article, and what actually says is that, okay, this video Gangnam Style was watched so many times. Okay, the views crossed more than 2 billion. Trust me, the number of views for this video is more than 2 billion views. As a consequence, that if you take any YouTube video, let's say, there will be a video, the number of views there will be a views value, isn't it? The number of views being number of times a video has been viewed, there is a number, and that number was actually kept in track by using a variable that is int variable integer of 4 bytes, as 4 bytes. So the maximum value it could store was this much. So when the number of views crossed 2,147,483,647, what happened is that the number tripped, and as a consequence the views turned out to be negative 1 or negative 2 billion something, negative 2 billion something. Okay, and this exactly happened. I mean, I don't know when exactly it happened. So as a consequence, as a consequence, what they did is, okay, the views turned out to be negative, and that is the first time the views by icon of that YouTube crashed ever. Okay, to rectify this problem, what they did is, okay, they just made a simple data change, and that will work out well. On the other hand, what they did is to rectify this error. Instead of using a 32-bit integer, they used a 64-bit integer. Okay, I mean, they just like you have a float and you have a double. The double which stores has twice the precision as that of the float. Okay, there's a higher value which is actually a 64-bit integer which has 8 bytes of integers. Okay, and they used that only for that particular video, and as a consequence, it can store up to this many number of views without any problem. Okay, let's see. This is 1,000, million, billion, trillion. Wow. God, this is such a massive number. It's not going to it's not likely to occur. I mean, this number is not going to likely to be hit. The number of views will not be hit even after 4 billion years. So they have to push this to a 64-bit signed number so that the number count remains normal. Now, if you just as a hobby, just as a out of curiosity, if you go and watch this, then you can just have a look at this. Clearly, this number we will be well off from this maximum limit that is possible. This is like the one very practical case of number overflow. I mean, data overflow that happened in the recent times. Okay, there are other technical cases as well, but this is something we will be most of the people will be able to relate with. Okay, I just put the link of this video, and I just put this link in the video description so that you can have a read through, and of course you can watch this kind of video as you want, but I'm not a supporter though. I'm not a big fan of this though. Anyway, that's all I have for you guys in this video. Thank you guys for watching. Hope you guys understood these concepts, and we might come across this every once in a while working with the video. So be careful and stay tuned, stay alert in these kind of cases. Okay, that's all I have for you guys in this one. Thank you for watching, and I'll see you all next time.